guys. So I got a little bit tired, but I still like to make a record. Yeah. So today let's given talk about a monotone function. So finish the continuous section for the advanced analysis. And basically, I want to prove the Froda's theorem. Okay, so Froda's theorem says that the discontinuous the number of discontinuity points for the monotone function is at most countable. It's at most countable. Okay, so this is the Froda's theorem. So that our goal is to given the definition of monotone function and finish the proof of Froda's theorem. Okay, so definition. So let's define a monotone function. So let's say f is defined on a b interval, and wait, let's first define the discontinuity, right? So let's suppose your f is defined to be a b, and then you consider x, which is larger than a, less or equal to b, and you can define a x plus. Okay, so x plus means that let's say if I say that f plus equals to q, so if ftn approach to q as n goes to infinity for all sequence for all tn in xb, such that tn approach to x. So this means that the right limit means that you try to approach x from a right? So every sequence in xb, you try to find all the sequence approach to x. If for every sequence tn approach to x, ftn approach to q, that I just write fx plus equals to q. Okay, then you can define the same thing for x minus, right? So x minus is just some points. All the sequence come from the left. Let's say come from ax, try to approach x. Okay, so obviously that clearly that all x belongs to AB. If the limit exists, so limit t belongs to x, ft exists. If and only if the left fx plus and fx minus exist, and they are the same. So the first condition is that both of them must exist, and the second condition is that they must be the same. So if 1 and 2 are true, then this is called this is the limit the same, right? So this is the same proof. But the same definition is the obviously results come from previous definition. Okay, so definition. So there are two kinds of discontinuity. One is the first kind. So the first kind is that if fx plus and fx minus exist, but fx do not okay, so there are three cases. The first kind means that the both are exist, right? But the limit do not exist. So I should say the limit does not exist. Okay, so this is called the first kind. So actually there are only two cases, right? The only case is that the case is that they are different, right? If they are different, then definitely you don't have a chance that the limit is. There is a case that they are the same, right? But maybe f of x do not define at that point. Okay, and also second kind. Second kind means that not first kind. Definition is not first kind. Okay. Yeah, there are some examples, but I think I don't have to mention. Okay, so definition, I think everybody knows about the monotone, right? So monotone function. So the strictly increasing means that when x greater than a, your f of a greater than f of x. This is called strictly increasing. If I put in here, I put equal sign here, then this is just increasing. And if a x greater than a, if you have f of a less greater than f of x, this is called strictly decreasing. if I put equal sign here, then it's just called a decreasing. Okay. Okay, so it seems like we didn't give any new information. So theorem. So for the monotone function, so when I start to prove anything related to monotone, I restricted my case into the strictly I force it to be the increasing function, right? So if you do decreasing, then it's similar. So let's do the increasing f. Let's say f increasing on AB. So theorem says what? Theorem says that the fx plus and f of x minus exist for every x belongs to AB. So this is the first statement. The second statement is that the suprema of f of t, let's say t less than a less than x, will become f of x minus less or equal to f of x plus, this is inf t xtb f of t. Okay, so this is the second theorem. Okay, so let's this is actually not difficult. So I think this is obviously by definition, right? So once you prove these two are the same, then you prove that the fx minus exists. Once you prove this suprema exists. Okay, and so first you need to show that suprema and the least are equal, and then you prove suprema exists. Then this will be the same as this, and the least will be the same, greater or equal to least by the monotone increasing. So actually, okay, so x minus is the same, right? So actually, I only need proof this and this, right? Okay. Let's see. Maybe I prove this. Yeah, I mean it's the same. Yeah. So once you prove suprema is the same as you do infinite. Okay, so let's maybe prove. Let's maybe focus on fx minus. Okay. Okay, so obviously the f is increasing, right? So this sup f of t a less than t less than x will obviously less or equal to f of x, right? So you know that f of t less or equal to x, right? So for all t less than x, right? If you take this, right? If you take suprema, right? So you get suprema of t a x, right? Will less or equal to f of x, right? Obviously. But so the remaining part is to prove that this guy is f of x minus. So I need to first show that fx minus this exists. Okay. So same reason, right? So epsilon given, right? There's so a at least. So let's say a is defined to be the sup of a less than t less than x f of t. So or epsilon greater than 0, then this is the suprema, right? So there exists upper bound, right? There's this delta greater than 0, such that when a less than x minus delta less than x, then you will have a minus epsilon less or equal to f of x minus delta less than equal to a, right? So you have this. Right, and 6, you know that f is monotone, right? So you get that f of x minus delta is less or equal to f of t greater than a, right? For any t less than greater than x minus delta less than x, right? So from here, and here, and these two, right? So you can combine all these, then you get the following. You get the f of t minus a is less than epsilon, right? So that means for epsilon greater than 0, left is this delta, right? Such that that delta for any x, you get x minus delta. You get x, you can always find t such that when t in this region, you always get this. So this is the same as any sequence you approach the limit from the left, you get the a, right? So which tell you that a should be the f x minus, right, by definition. Okay, so yeah, so once I prove that this is exactly the same as this, then I know this exists, right? The reason is that this is the suprema, and this suprema is already bounded by f of x, so the suprema exists, right? So here basically we just prove all these parts, and these parts are the same. Okay. Okay, so yeah, I think the final results that I need to do is the Froda's theorem. Okay, so once we prove this, we can prove the Froda's theorem. Okay, so Froda's theorem. So basically, given a monotone increasing or decreasing function, the discontinuity, so discontinuity point of f at most countable. Okay, so let me just there's an example that so this increasing or decreasing is very important, right? Otherwise, that I can have a function that f of t such that if t belongs to rational, like if 1 is to not rational, it becomes 0, right? So in this, so now every rational points can contain infinite irrational points approach to it. So that means there's any points on real will not be continuous, right? So the number of the discontinuity, let's define d of f of, let's say d of f is the number of discontinuity. This set is exactly the number of r, right? So every point is not continuous. But if it's increasing or decreasing, then it must have at most countable point. Okay, so this is equal to Froda theorem. Okay, so let's focus on the first case is when I is a, let's say we focus on the function defined on the closed interval. And from our previous that we get f of a, right? The let's say equals f as a plus, right? Equals to this, equals to this, equals to this, equals to this, right? This is what we get. Okay. Okay, so suppose that alpha greater than 0, I take the points which is discontinuous. Let's say suppose I get x1, x2 up to xn, which is a jump, such that so jump means that right and left are different, such that fxi plus minus fxx minus is greater or equal to alpha. I don't want to. Okay. So suppose I take the n jumps such that it satisfies this condition. Okay, so remember, start from up to now, I don't know how many n it is. Right? I don't know. I just say that, oh, I just pick n of them. Suppose I have I have a lot of them. I pick the first n, or okay. Suppose I have a lot of them. I just pick the first n or something. I just assume that I get n of them. Okay. Okay, so and easy to check that the f of b minus f of a, right? So this minus this will greater to equal to x f xn, right? Minus f of x1 minus, right? Because this is just that, right? This, right? So by the monotone condition. Okay, then you can write it as fx n plus minus f of n minus because of f, let's say this can be written as x as minus minus f of x 1 minus. So basically, yeah, this is just the first step. So let's maybe write as more systematically. Let's say write as this. I can write as y from 1 to n, fxi plus minus fxi minus. Right, so plus I from 1 minus 1, fxi plus minus f of I plus and minus. Okay, you can check it. Okay. Okay, and you don't care about this term, right? Because this term is basically positive. So by definition, this is just there's a order, right? So this guy is greater or equal to alpha, right? So an alpha. Okay. So which tell you that this is f of b minus f. This is less or equal to f of b minus f of a. But which tell you that the n is less or equal to f of b minus f of a. divided by what? Divided by alpha, right? So which you tell you that given alpha, the number of jumps greater than alpha at most have f of b minus f of a alpha, right? So that's so now we can finish proof, right? Let's define a set of S1, which is a point between the open interval such that the fx plus minus fx minus is greater or equal to 1, right? So that means there is a discontinuity, and the discontinuity jump is greater or equal to 1, okay? And we already proved that this is finite, right? For any alpha, we just prove this is finite, right? So let's take in general define Sn, which is also x in the open interval, such that fx plus minus fs minus greater or equal to 1 over n minus 1. Right, so n is greater or equal to 2, greater or equal to 3. Yeah, I think 2, right? 2 is not, oh, sorry, that should be less, sorry, because I already defined 1, right? So it should be less. Yeah, so for n greater or equal to 2. And less than, and then okay, so let me just redefine. So Sn defined to be the open interval such that fx plus minus fx minus less than 1 over n minus 1, and greater or equal to 1 minus n. Right, so this I restricted the jumps into can maybe less than this and the greater or equal to this. So obviously that every jumps, so all the jumps, so all the discontinuity, right? All the discontinuity is just the union of Sn from 1 to infinity, right? Because the jump greater than 1, I already get it, and the jump less than half, greater or equal to 1/3, I get it, and less or equal to 1/3, and 1 divided by 4, I get it. And then now you see by definition, these guys are disjoint union, right? So usually you can write a disjoint union. Disjoint union, okay? And then we prove that for each one is finite, right? So since each Sn is finite, so this guy called D at most countable. Okay, so we prove that given AB, if f is defined on the AB interval is a monotone, then the discontinuity is at most countable. Right, so this is the Froda theorem, and you can easily check that if you change this to be the whole real number, then it still be at most countable, right? Because if you get real number, I can write real number as minus n to n and from 1 to infinity. I can use the larger interval to cover this. But for each one, you still get countable, right? So the countable union of the countable, which is definitely still countable. Okay, so that's it. Okay, so this is the proof for that theorem. And next time we can talk about the limit at the infinity or something, which is very easy. Then we move to the derivative. Okay, so see you guys in the next video.